In this question, we need to evaluate the sum from n equals 1 to 100 of log base 2 of 3 to the 1 minus n. So I think a couple of things should be at the forefront of our minds. Firstly, whenever we see a log in a TMUA question, we should be thinking about log rules. In particular, I've got log with a power in it here. That brings to mind the log rule that log of a to the n is n log a. I can bring a power out as a multiple. Another thing is that sigma notation, while it's really useful for packaging up big sums in clear, compact notation, it can also sometimes make it harder to see intuitively what's going on. So what I am tempted to do is let's just expand out a few terms of this sum explicitly and see what happens. So the first term, when n is 1, I get 3 to the 0. And then with each subsequent term, I guess my power drops by 1. And that's going to keep happening until at the very end I've got a power of minus 101, or rather minus 99 in fact, when n is 100. So I think now it's written like this, it's a bit easier to see what's going on because I can now use this rule to pull all the powers out. I'm going to have a common factor of log base 10 of 3 and a big bracket, which is going to be basically just an arithmetic series. Much harder to see that when it's originally written. So certainly sigma notation is useful, but don't be afraid to expand. So now, if I bring the powers down, obviously the 0 comes down, completely kills that term. This I bring down a minus 1. This I bring down a minus 2. Next one I bring down a minus 3. Minus 3 there. All the way down to eventually bringing out this minus 99. So now I can pull out, I guess, the common factor of minus log base 10 of 3, and what I'm left with is 1 plus 2, note that because I pulled out the minus they all become positive, plus 3 plus 4 all the way up to 99. So now all I have to do is evaluate the contents of that square bracket, but that is just a simple arithmetic series. So we've got first term, I'll call it A equals 1. We've got last term, I'll call it L equals 99, and we've got 99 terms. So using the formula for the sum of the first n terms of an arithmetic progression, n by 2a plus L, where n is the number of terms, a is the first term, L is the last term. You can, if you prefer, use n by 2a plus n minus 1d, where d is the common difference. They're the same as each other. You must remember them. There's no formula booklet for this exam. What we see is that the sum from 1 to 99 is going to be 99 over 2 times 100. So that gives me minus 100 over 2 is 50. So minus 50 times 99 of log base 10 of 3. So 50 times 99 is obviously 1 less than 50 times 100. So that's going to be minus 4950 log base 10 of 3. So the correct answer is A. Not too hard once we realised we certainly wanted to use log rules because there's a logarithm involved and they love them on the TMUA, and also that expanding out of sigma notation could make it much clearer what was going on. In this question, we're told a family of quadratic curves is given as here. So by family of curves, what they of course mean is that for each choice of k, this is a different quadratic. So we've got lots of different quadratics, and we can pick out one in particular by choosing the value of k, where k is a real number and yk is of course a function of x. We're told that all of these curves are sketched, and the point with the lowest y coordinate among all the curves, yk, is ab. We need to find the value of a plus b. So I guess a sensible starting point is surely to find the minimum of yk in terms of k. So for each one of these quadratics, there's going to be a lowest point, that's the minimum, and we can actually see that very easily because of the completed square form they've given us this thing in. So surely if we start by asking for each yk what's the minimum, obviously the overall minimum is then going to be the smallest of those minimums. So it's like step 1, we can find the minimum of yk, and that's going to be in terms of k because we're not fixing what k is yet. So that gives me the value of the minimum for each individual quadratic, and then we could find the smallest value this takes as k varies. So essentially in this step, we're finding where yk is smallest as you vary x, as you look at all the points on that particular curve. And then we're saying, okay, now looking across the different curves as I vary k, which one has the smallest minimum? So I think this sort of two-step process seems to be appropriate. So first of all, we can see very easily, because this is in completed square form, that yk has obviously got vertex when x is k by 2, so that vanishes. And then the minimum value is going to be this stuff. So k squared by 2 plus 4k plus 3. So I guess this is going to be a, right? Whatever k turns out to be, I plug k in, k by 2 is going to be the x coordinate of my minimum, because that is where the vertex lives for each of these quadratics. Now to find the minimum of this thing, I can just view this as a function of k in its own right. So if I write f of k equals a half k squared plus 4k plus 3, I could complete the square on that, but to minimize it, it's probably easier to just differentiate. So differentiating, I get k plus 4. So that means that k equals minus 4 gives my minimum, because obviously the turning point of a positive quadratic is going to be where it's minimized. So I know that the quadratic which has the lowest minimum is the one with k equals minus 4, but that's brilliant because now I know I can just plug minus 4 back in. That thing's going to be minus 2. That thing is going to be 16 by 2 minus 16 plus 3. That's 8 minus 16 plus 3, which is minus 5. So overall, I've got minus 5 for my actual value of the minimum. That's B. And I've got minus 2 for my x coordinate of the minimum. That's A. So A plus B is going to be minus 7. So correct answer is D. So it's really helpful to realize that obviously the overall minimum is going to be one of the turning points, right? The vertex of one of the quadratics. And then we see that we can break the problem into these digestible chunks. First find the minimum of yk, and then look for the minimum of that as k varies. In this question, we're told that a cubed plus 2 by b cubed times 2 by a cubed minus b cubed equals root 2, and we need to find the smallest possible value of a b. So this looks pretty daunting. It's not really obvious what we ought to do, how we could possibly even begin to ask for the minimum value of AB. So if the first step isn't obvious, we should just sort of do the only thing algebraically that we can. And that, to me, seems to be expand out these brackets. Maybe something good will happen if we expand the brackets. So I'm going to get, well, this term's going to give me a 2. And then I get this, which is minus a cubed b cubed. And then I get plus 4 over a cubed b cubed. And then I get minus 2. Now, actually, that's quite good for two reasons. Firstly, notice that the constants have vanished. Secondly, notice that a and b are only appearing in this thing in the combination a cubed, b cubed. Well, that's just ab all cubed. So presumably there's a sort of hidden polynomial type thing going on. If I substitute maybe u equals a cubed b cubed, I can easily solve this thing to find what a cubed b cubed is, and I can use that to see what ab is going to be. So actually this looks pretty hopeful now. So sometimes it is just a matter of sort of jumping in and doing the algebra, even if it's not obvious exactly where it's going to take you. So having made that substitution, just to keep things tidy, the equation reads minus u plus 4 by u is root 2. Sorry, that should have been a 2, not a 3. This is clearly going to turn into a quadratic if I just multiply through by u. So then I've got, if I bring everything onto the right, u squared plus root 2u minus 4 is 0. Not much hope of factorising that, I think, but we can use the quadratic formula to see that u is going to be minus root 2 plus or minus the square root of b squared minus 4ac. Well, b squared is 2. That's going to be plus 16 all over 2. Now, of course, that's root 18, but 18 is 2 times 9. 9 is a square number. So I can pull out a 3, and I get that is 3 root 2 over 2. So there are two possible values for what a cubed b cubed can be. Now, because x cubed is an increasing function, the bigger the number I cube, the bigger the number I get out. If I want AB to be as small as possible, I obviously want A cubed B cubed to be as small as possible, which means I definitely want to pick the minus root in order to minimize AB. So if I'm doing that to minimize AB, that tells me that A cubed B cubed, the minimum that can be, well, minus root 2 minus 3 more root 2s is going to be minus 4 lots of root 2 by 2, which is minus 2 root 2. All I have to do to find AB is to take cube roots. So maybe to ease that along, we should write this in power notation. Obviously, that is going to be 2 to the 3 over 2, because this is 2 to the half, this is 2 to the 1. So taking cube roots, I'm just dividing any powers by 3, because I'm raising to the power of a third. So then I'm going to get that AB min, the smallest it can be, this of course is the minimal value, because we've taken the minus root, is going to be minus 2 to the 1 over 2. That is just minus root 2. So the correct answer is A. So often in these problems, as long as you have the courage to just start doing some algebra, the problem does unravel itself very quickly. But it does look very daunting when you first look at the equation that you're actually given. In this question, we're told a circle has centre O and radius 6. P, Q and R are points on the circumference, with angle POQ being obtuse, so it's at least pi by 2 in radians. We're told the area of triangle POQ is 9 root 3, and we want to find the greatest possible area of triangle PRQ. And I guess possible suggests that the area can vary. Presumably the variation is going to come from choosing where to put the point R. So let's begin with a nice big sketch that will make things much easier than if we're just trying to visualize everything in our heads. So we've got O. Now in terms of positioning P and Q, while I guess it doesn't have to be the case that there's a kind of horizontal line of symmetry, because we're only interested in areas, I'm quite at liberty to rotate my figure round to make it so that I have got this kind of line of symmetry for P and Q. Because we're only interested ultimately in finding areas. Areas don't care about rotation. So I'm free to draw my figure like this. I know these are both 6 because of the fact they're radii. And then I guess this angle, this obtuse angle POQ, I may as well call it theta so that I can mark that on. Now we're told in the question that the area of this triangle is going to be 9 root 3. Surely then I can write down an expression for the area of this triangle in terms of theta and use that to find theta. That should be very helpful when I come to consider the triangle PRQ. So I guess using half AB sine C, the area is going to be half times 6 times 6 times sine theta. That is what we know is 9 root 3 because we're told the area of that triangle is 9 root 3. So 6 times 6 is 36, over 2 makes 18, so that means sine theta is going to be 9 root 3 over 18, which is root 3 over 2. Now that's fantastic news because without a calculator, we can't generally take inverse sines very easily, but root 3 over 2 is one whose principal value we memorize. So the principal value for this is going to be pi by 3. We know that sine of pi by 3 is root 3 over 2, but of course that's not an obtuse angle. So we have to use the symmetry of the sine graph to deduce the other. So you see there are two values from 0 to pi which will work. If this is pi by 3, then by symmetry the other value, because this distance here is the same as this distance here, that's going to be pi minus pi by 3, which is 2 pi by 3. So you could have identified the other value alternatively using a cast diagram with a circle, if you prefer to do it that way, or you could have just used the algebraic symmetry result. Sine of pi minus theta is always the same as sine theta, which is really, if you think back to lesson 3 of our TMUA primer course, a manifestation of the reflective line of symmetry of the sine graph in pi by 2. So because it's obtuse, we know that theta is really 2 pi by 3. At this point, we can actually put that in our figure to start simplifying things a bit. And now we need to think about the triangle PRQ. So to make PRQ, I'm going to put another point on and join them up. And I guess it's pretty clear by symmetry. If I want that to be as big as possible, I want to put R in this kind of symmetrical arrangement. So I want to put it so it's aligned with where O is. In other words, it's equidistant from P and R. Now, this is a multiple choice exam, so you're not expected to prove that. But if you just eyeball the figure and move R around a bit, so here's one example of R. If I put R, say, there instead, you're clearly getting something smaller for triangle PRQ. It's generally true that symmetric arrangements will maximize things. And that's actually why there's so much symmetry in nature, because whether in biology, where evolution's trying to optimize things, or in physics, where the sort of mature way of formulating things is in terms of minimizing a quantity called an action, there's lots of ways in which nature has to try to optimize, to minimize or maximize something. So if in doubt about a minimization or maximization problem, the symmetric arrangement is always a safe bet. So this angle, I guess we know, is pi by 3 by a circle theorem, right? There's a circle theorem that says the angle subtended at the center is twice that subtended at the arc. If you need review of circle theorems, do take a look at lesson 5 of our TMUA primer course. So now we just need to find an expression for this area. So we don't know these side lengths. I mean, we know that these are 6. Well, if we've got a horrible area, it's usually best to try to divide it into smaller chunks. So maybe this triangle I can split. So I've got the triangle POQ already, and then I've got these other little triangles. Now that's pretty good news, because these other little triangles, we know the side lengths, and we can also deduce about the angles, because by symmetry, that cuts that into half of pi by 3, which is pi by 6. By isosceles, this must be pi by 6 as well. And then by sum of angles in a triangle, you've got to make pi overall. That must be pi by 3. By symmetry, that's pi by 3. So now this is really easy, because we know that this thing had area 9 root 3. This thing is going to have area half A, B, sine C. So the angle that is made with the 2 length 6 sides is pi by 3. Sine of pi by 3 is root 3 over 2. So we get 36, 18. We actually then get 9 root 3 again. And then by symmetry, that's going to be 9 root 3 as well. So this big triangle, PRQ, in the optimal arrangement is just split into 3 little triangles, each of which have area 9 root 3. So that means the total is going to be 3 lots of that, which is 27 root 3. So the correct answer is D. Not too difficult when we draw a sketch, but if you try to do this all in your head, you won't get very far. In this question, we're told a rectangle is drawn in the area enclosed by the curves P and Q, where P and Q are given here, so they're nice simple quadratics, such that the sides of the rectangle are parallel to the X and Y axes. We need to find the maximum possible area of such a rectangle. So let's begin with a sketch. This is clearly a problem of a very geometric nature, so if we have a sketch, it may be clearer how we ought to proceed. Moreover, it's not going to be very difficult to draw a sketch because these are both very simple quadratics. So let's find the x-intercepts. I mean, this one here, obviously the x-intercepts, if I pull out a factor of 2, I've got 2 lots of 4 minus x squared. So I'm going to have x-intercepts at plus and minus 2. So 2 minus 2. And the y-intercept of this one is up at 8. It's not important that it's to scale. You'll notice that mine is not, but that's not going to be a problem. So P is something like this. I guess once we know the x-intercept, the y-intercept, we see that the vertex is clearly on the y-axis by symmetry for this thing. So it's pretty easy to draw. So that's y equals P of x. What about Q? So Q is a U-shaped quadratic, and it's obviously got x-intercepts at plus or minus square root of 2, which is about 1.4, and y-intercept at minus 2. So again, doesn't matter if it's to scale, I'll put minus 2 there. Obviously, root 2 and minus root 2 are both less than 2. So I'll have to make sure I've got the appropriate relative positioning, even if the scale isn't necessarily quite right. So that's going to go up like this. And you see the whole figure has got this symmetry about the y-axis. That seems likely to be relevant. I guess we should surely also like to find the intersection point might be important, but maybe we should leave them for now. It's a note that if I'd drawn it properly by symmetry, they'd be at the same height. It's not entirely obvious that we need those, actually. I mean, we could try to find them. Let's set that aside for the moment. Because when we start drawing in these rectangles, what can it look like? Well, I guess what you can see is, although in principle, you might think that you've got 4 choices to make for a rectangle, the position of each of the vertices. Because it's got to touch against these parabolas, once you pick one vertex, that actually fixes the location of all the others. So that is quite interesting, because what I can then do is if I introduce a single parameter for example, the x-coordinate of the upper right corner, I can find all 4 other vertices in terms of that parameter, and I can then write down a formula for the area in terms of one variable. So that seems really very useful indeed. So let's just say that the x-coordinate of the upper right corner is going to be, let's call it, what should we call it? Let's call it A. So say that the upper right corner, because if I find an expression for the area in terms of A, I can then minimize it as a function of A. So say the upper right corner is at x equals A. So clearly the upper right corner lies on the curve P. So because it lies on P, if my x-coordinate is A, my y-coordinate must be 8 minus 2a squared. But then, by symmetry, this thing over here is at the same height, but it's now got the negative version of the x-coordinate. This one has got the same x-coordinate again, but now the y-coordinate is given by the other curve, Q. So to find the y-coordinate of this vertex, I'm going to plug A into Q. That gives me a squared minus 2. And then this vertex, similarly, is obviously going to have x-coordinate minus A because it's horizontally aligned with this one. And I can get the y-coordinate by plugging minus A into that, again giving me a squared minus 2. So that means I can write down my area as a function of A, because clearly let's see each dimension, in terms of my width, I've gone from minus A to A, so my width is 2A, and in terms of my height, I've gone from a squared minus 2 up to 8 minus 2a squared. So that means my height is going to be the top minus the bottom, which is going to be 10 minus 3a squared. So this is glorious news, because now I know that my height is 2a 10 minus 3a squared. That's a simple function of A. In fact, it's just a basic cubic, and I can now study when is this thing at its largest. So notice that we need A to be positive because we've chosen to define A as the coordinate of the upper right corner. This is a negative cubic, so for big A it goes down. That makes sense. So that there is going to be a unique maximum for positive A. So let's study this thing. Expand out the brackets, we get minus 6a cubed plus 20a. We're surely interested in the turning point. I mean, you could also check the ends of the interval, but when A is 0, our area is nothing. And when A gets really big, we get a negative infinite area. So it's obviously going to be the turning points that do best. Differentiating, minus 18a squared plus 20 is 0. So that means a squared is going to be 20 by 18, divide through by 2, 10 by 9. So that means that A is going to be plus or minus, but we've got to take the plus based on the fact we defined A that way, root 10 over 3. So the only turning point I have for positive A is at root 10 by 3, because the ends of the allowed interval, A is 0 and A really big, clearly did a rubbish job of maximizing. This must be what we want. So then we just have to plug that into our expression, and we get minus 6 lots of, now that thing cubed, 2 of them are going to give me a 10 over 9, and then I get another one, root 10 by 3, and then I've got plus 20 lots of A, so that's going to be plus 20 by 3 lots of root 10, that's my 20A. Okay, so I can cancel this 6 with that, and it becomes a 2. So I've got minus 20 by 9 root 10 plus 20 by 3 root 10. I guess I can put that over a common denominator of 20 by, well, common denominator of 9. So that is going to be 60 by 9. 60 by 9 minus 20 by 9 is going to be 40 by 9 root 10. And hopefully that's an option. Yes, so the correct answer is H. So a sketch really helped, because then we realised that we could capture the entire ability of the rectangle to vary with a single parameter so that it becomes a simple function maximization problem. And I don't think that would have been obvious without a nice clear sketch. In this question, we're told that the solutions to 7x to the 4 minus 6x squared plus 1 equals 0 are plus minus cos theta plus minus cos beta for some theta and beta presumably. And we want to decide which of the following quartics has solutions plus minus sine theta plus minus sine beta. So surely we should begin by trying to think about how the old solutions relate to the new solutions, because we're trying to find essentially a quartic equation with solutions related to the originals. Well, let's ask specifically how are they related? And I think the answer to that is quite straightforward. So we have this identity that sine squared plus cos squared of anything is always 1. So in particular, that means that I know that sine squared theta plus cos squared theta is always 1, and I also know that sine squared beta plus cos squared beta is always 1. So how can I express my new solutions that I want in terms of my old solution to see exactly how they're connected? Well, that's easy. I know that sine squared theta is 1 minus cos squared theta, and then the fact that I've got a squared rather than the original is just capturing the fact that here I'm really looking at both the plus minus case at the same time. And similarly, I know that sine squared beta is 1 minus cos squared beta. Now this motivates a really slick solution to the problem. Because if I make the substitution, let's just let u squared be 1 minus x squared, I know that when I have a solution in x, because obviously a solution in x is going to be one of these, my solution for u squared is going to be exactly these things, right? So for example, when x is plus or minus cos theta, that means that in terms of my new variable u is going to read 1 minus cos squared theta, which is just sine squared theta. So by design, the solutions in the new variable in u are going to be precisely what we want, plus or minus sine theta. So this is a really powerful approach. If you've got two equations where you want the solutions to be related, you can implement this by making a simple substitution. This is a technique well worth learning, and it is discussed in quite a lot of detail in lesson 1 of our TMUA primer course, so have a look there if you haven't already. So let's make this substitution and just see what happens. So if u squared is meant to be 1 minus x squared so that the solutions are related in the appropriate way, our equation reads, well, let's see, x to the 4 is x squared squared, so x squared is going to be 1 minus u squared, just inverting that relation. So 1 minus u squared squared. And then minus 6 squared is minus 6, 1 minus u squared. And then we've still got just the plus 1 equals 0. So we know that by design, is that 6? Yeah, plus 1 rather. So we know that by design, the solutions to this quartic in u are exactly what we want. We've designed it that way by making that substitution. So now all that remains is to expand out the brackets. So minus 2u squared plus 1 minus 6 plus 6u squared plus 1 is 0. So that means we get 7u squared, and then I get minus 14 plus 6 makes minus 8u squared plus 7 minus 6 makes 1 plus 1 makes plus 2 equals 0. Now, if you look at the options, you'll notice that they use x rather than u, but that doesn't matter. The letter doesn't matter, because whether I use u or v or z or x or y or a little picture of a burger, whatever symbol I use, the solutions to the equation are the same. By the way, sorry, slight typo, that was obviously meant to be 7u to the 4. So whatever letter we're using or symbol we're using, the solutions are the same. So this obviously is going to have the same solutions as this. The only reason we changed to u was to make it easier to implement the change of variables that made sure the solutions were appropriately related. So we're looking for 7x to the 4 minus 8x squared plus 2 equals 0. And that means the correct answer is B. In this question, we are given a diagram with a triangle which has some sides and some lengths marked on, at least in terms of x. we need to find the complete set of values of x for which there are two non-congruent triangles with such side lengths and angles. So I guess we should probably introduce a letter to describe the one side length we don't have. Let's call it d. Always helpful to give unknown quantities a letter so that we can play with them algebraically. Now I guess I can try to study d in terms of x by using the cosine rule. I can't use anything else really with this triangle. For example, Pythagoras is out because it's not right angled, but we have to be slightly careful. So for example, if I apply the cosine rule and I show that for a particular value of x, maybe there are two possible values of d, that doesn't necessarily mean I can produce two different triangles, because if I give you three numbers, there's no guarantee that you can actually build a triangle with those side lengths. So in order to possibly build a triangle, we need what's called the triangle inequality. This is something you must know for TMUA. So we need, in order for three side lengths to actually be possible side lengths of a triangle, the sum of the shorter two, sorry, I wrote the wrong around, must exceed the longer. So the sum of the shorter two sides in a triangle must exceed the longest. So we may get sort of false solutions. We might think we found a value of d that works, but if we check, if the three sides don't then obey this, we'll have to discard it. Maybe that won't become relevant, maybe it will, but we should bear it in mind. Okay, let's apply the cosine rule. So I guess by the cosine rule, we're going to have to use the cosine rule such that this is the angle involved because it's the only angle we know. So we get this thing squared, x minus 1 squared, is going to equal the square of the other two sides. So we get a d squared, and we get the minus x squared plus 6x minus 5 all squared. And then we get minus 2 times the product of those two side lengths times cos of the angle, cos 30. Cos 30 is just root 3 over 2. So I guess bizarrely, this thing is secretly a hidden, well, not even hidden, it is a quadratic in D. Yes, the coefficients are in terms of x, but if we're taking the perspective that we want to find d in terms of x, this is a quadratic in D. So we've got this minus x squared plus 6x minus 5 all squared. So d times, well, 2d times root 3 over 2 is going to be minus root 3 x minus x squared plus 6x minus 5d. So let's collect terms all on one side as we usually would with a quadratic. So we get, let's bring it all on the right. This is our d squared term. This is our d term. And then our constant term is going to be this. There's no point expanding out all these brackets yet because it's obviously going to get ugly if we do. We might want to in a moment. Okay, well, I guess at this point, the only thing I can really do is apply the quadratic formula. It's going to be ugly, but maybe we'll learn something. Let's just see what happens. And sorry, of course, that's got a square on it. Okay, so let's just apply the quadratic formula, see what we get. So d has got to be root 3 minus x squared plus 6x minus 5 plus or minus the square root of 3 lots of that thing squared minus 4 times that stuff. So that's minus 4 more of those gives me minus 1 of them overall. So overall I'm going to get minus 1 lot of this. And then minus 4 on that gives me plus 4 of them. All right, so, and then that's all over 2. You might be worried that x, of course, the coefficient is not constant and we've used the quadratic formula. But if you think back to the proof of the quadratic formula, it's just essentially completing the square. It nowhere uses that the coefficients are genuinely constant. It's just algebraic rearrangement. So this is all totally allowed. Now, obviously studying this in terms of general x is going to be way too difficult to make any serious progress. But we have to remember this is a multiple choice exam. So we can pick some simple values of x and see what happens. For example, if I find for a particular value of x there are no values of d that work, there's no congruent triangles I can possibly draw. No, well, congruent or non-congruent, there is just no such triangle. If I only get one possible value of d, well, by the SSS criterion, side, 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 if there's only one possible value of d, the sides are all uniquely fixed. There's only going to be one type of non-congruent triangle I can draw, because anything else with the same sides, all three, would have to be congruent. So we can play with some specific numerical values. Why don't we start by trying x equals 2? I mean, we don't use x equals 1 because 1 isn't included in any interval. But these three say 2 should be fine. These three say it shouldn't. So let's try x equals 2. And we may as well start by looking specifically at what's in the square root, because obviously if that's negative, that tells me a lot straight away. So the square root thing is going to be, let's see, well, at 2, that's going to be minus 4 plus 12 makes 8, minus that makes 3. So I'm going to get minus 3 squared. And then that there is going to be a 1, so I'm going to get plus 4, which is clearly no solutions, right? The thing inside the root is negative. So at x equals plus 2, there's no value of d that's possible. So there's obviously no triangle I can draw. Certainly not two non-congruent triangles then. So anything allowing 2 gets ruled out. That's pretty good. We're down to pretty decent odds if we had to guess. Now, do the remaining options disagree on any integers? Well, this one says 4 is fine. These say it's not because they're strict inequalities. So let's try x equals 4 next. So again, rather than focusing on the whole expression, because it might be enough, let's just look at the root. So when x is 4, that's minus 16, plus 24 makes 8, minus 5 makes 3. So I actually again get minus 3 squared. And then this thing becomes, well, that's going to be 3 squared, which is 9. 4 lots of it makes a plus 36. So that gives me, I guess, 27, which is 3 root 3 when I take the root. So that's fine. We've not gotten a negative thing inside the root anymore. So it looks like there are possible values of d. But before we decide, that means this value might be fine. I mean, of course, even if we find 2 positive d, we have to then check the triangle inequality. But before we decide there's any chance this is fine, we better make sure both values of d are really positive by going back here. So remember we saw this quadratic was 3 at this value. So I'm going to get a 3 root 3 from that. So I'm going to get d is 3 root 3. Hang on a minute. 3 root 3 plus or minus 3 root 3 over 2. But that means that the minus root is going to have d as 0. And I'm not allowed to have a 0 length for one of my sides. Then the triangle degenerates down to just a line. So actually x equals 4 is also has no chance of working because there's only one possible value of d. It's going to be the value with the plus. So that means that all 3 side lengths for x equals 4 are fixed to take particular values. And then by the side criterion, any triangle which we could draw is going to be congruent. If you do want a review of the conditions for congruency, by the way, take a look at lesson 5 of our TMUA primer course where that's all covered in lots of detail. So anyway, we see that x equals 4 is disallowed. That's a bit annoying because if it was allowed, it would have ruled out everything except for e, but now we've still got 2 options. Now, this is a bit annoying because there are no longer any integer values which we can check. And I don't particularly fancy plugging in fractional values. But I guess there's a bit of a get out of jail free card here, which is that these inequalities are strict. So when we have a strict inequality, it's a bit of a strange thing. For example, saying that x can be bigger than 3, I can make x as close to 3 as I like, right? So I can let x be 3.00 followed by a million zeros, then 1. That would be fine. In other words, I know that at x equals 3, I should be right on the cusp of being fine. If I increase x even slightly, it would work. So D is telling me, it's not telling me 3 should work, but it is telling me x equals 3 should be on the boundary of working. Now, actually, we just saw that a minute ago. So we saw that for x equals 4, we got one of our values for D was 0. That's right on the boundary of working because presumably if I vary x by a tiny bit away from 4, this d equals 0 would become a tiny positive value. So having d equals 0 is one way that we can be right on the cusp of having an extra value that works. So we know according to d we should be on the boundary of working. So that means either we should have d equals 0 for one solution, or I guess another way that we could be right on the boundary of working would be if the discriminant was 0. Because if the discriminant was 0, again, if I change x by the tiniest bit, that would be expected to give me a second solution. So if we check what happens at x equals 3, we'll see whether we are on the cusp of working or not. And that should let us rule things out. So let's try x equals 3. So in terms of our root, well, the quadratic factor is going to be minus 9 plus 18 makes 9, minus 5 makes 4. So we get minus 4 squared. And then we've got, well, x is 3. That's going to be a 2 squared. So that's going to be plus 16. Ah, that is 0. So discriminant is 0. That tells me surely that I'm on the boundary of working, right? Because if I vary x by a tiny bit, what I'm then expecting to see happen is that the discriminant changes a tiny bit and it's enough to make it go positive. So based on the fact that looking at that, x equals 3 really does look like it's on the boundary of working, it must be D, which is the right answer. In question 18, we're given that f of x equals x squared, x minus 1 squared, x minus 2, and g of x is minus p, x minus q squared, x minus r squared, where p, q, and r are positive and q is less than r. We need to find the set of values q and r that guarantee the greatest number of distinct real solutions to the equation f of x equals g of x for all p. So I think this is clearly crying out to be solved graphically, because then maximum number of solutions just corresponds to maximum number of intersections. Let's start by sketching f, because it's the one that doesn't depend on any parameters, it's fixed. So it's going to have an x-intercept, but specifically a touching point at x equals 0. So if the power of the factor for the solution is even, you're going to touch the x-axis rather than cutting it. You can find discussion of that in lesson 1 of our TMUA primer course. We're also going to touch at 1 for the same reason, because of that factor, and then we're going to cut at 2. It's obviously a positive quintic, so if you expanded out the brackets, you can see the highest power of x term is going to be a plus x to the 5. So positive polynomial of odd degree, it's going to go up to plus infinity when x gets really big and positive, down to negative infinity when x gets really big and negative. So it's going to have to do something like this. And you can see the number and nature of turning points is essentially fixed by how the x-intercepts behave. I mean, we haven't really demonstrated whether or not these turning points are higher or lower than each other, but I don't think that's likely to be important. This sketch should be detailed enough for our purposes. Now, what about this? So this is a positive quartic, and it touches at q and at r. So how can I make sure I have as many solutions as possible? Well, in fact, sorry, it's a negative quartic because of minus p is positive. So we know it's got to go down to negative infinity when x gets really big in a positive or negative sense. I mean, isn't it kind of obvious that if I want to cut as many times as possible, I definitely want one of my touching points to be there so that I've got to kind of burst through that thing. But then it would be good if my other one were in here, because that's going to force me to kind of burst through again. So it seems pretty clear just from a sketch that in order to force the maximal number of intersections, that's how it's going to go. Now, actually, things are even better than that, because remember, the pink curve is a quintic, the red curve is a quartic. So we know that when x gets big enough, the quintic is actually going to have overtaken the quartic, which means really it's going to be something more like this, and it's going to overtake it again. But actually that will be the case regardless of our choice of parameters, because it's always true that a quintic will overtake a quartic. So it's pretty clear from the sketch. In order to maximize intersections, I want my earlier solution to live between 0 and 1, and I want my second solution to live between 1 and 2. My sooner solution is q, so I want q to live between 0 and 1. And I clearly also want r to live between 1 and 2. We're already told p, q, and r are positive, so that becomes redundant. And I guess we then see. Correct answer is B. In this question, we're told a circle C1 is defined as x squared plus y squared equals 25. So that means we're going to have center 0, 0 and radius 5. We're told a second circle has radius 4 and centre AB, where A and B live between -2 and 2 and -3 and 3 respectively. And if the centre of C2 is equally likely to be anywhere in this given range, so you just pick a point at random, we need to decide what's the probability that C1 and C2 intersect. Okay, so I guess before we even start thinking about probabilities, presumably we'd like to derive a condition which A and B, the value of A and B chosen, must obey in order to have an intersection. So it's well worth memorising the condition for two circles to intersect. This is covered in lesson 4 of our TMUA primer course, but I won't assume you've seen that here. Let me just remind you of what that formula is. So if two circles have radii, let's say R1 and R2, and I'll choose to label it so that R1 is the bigger of the two, and the centres are D apart, then the condition for intersection, so I'd recommend memorising this, and I won't go through the sort of full derivation of it here, you can see the primer course for that, but I will just briefly outline where it comes from. So the condition for intersection, nice simple condition to remember, is that the separation of the centres has to live between the sum and the difference of the radii. So well worth memorising that. Now where does this come from? I think this part is quite obvious, because if the separation of the centres was bigger than the sum of the radii, that means that obviously the circles wouldn't be able to stretch across the distance and meet. So if your centres were separated by 50, but the radii together only added to 10, obviously they're not going to reach each other. This is the bit of the condition that's less obvious, so I outline exactly where it comes from, as in deriving that specific formula in the primer course, but essentially that's there to prevent a situation like this, where the circles have actually, well, one has completely engulfed the other. So this condition prevents you from having something where they're totally separated and just can't stretch the distance, and this prevents you from having an engulfing situation. So well worth memorising that. It is frequently useful in admissions tests like the TMUA. So in our particular case here, obviously the separation between 0, 0, the centre of this one, and AB is going to be square root of A squared plus B squared, and then the sum of the radii, 4 and 5, is going to be 9, the difference is going to be 1. Okay, now I can square across this inequality to simplify it. It's okay to square an inequality as long as both sides, or in this case all three sides, are positive. Because x squared is an increasing function for positive values. The bigger you put in, the bigger you get out. That means if I apply it across an inequality, the inequality is going to remain true with the inequality sign pointing the right way. So that means this is really equivalent to this. So I guess we've got two things at once here. This bit is clearly saying that AB is outside the circle with radius 1, centred at the origin. So A squared plus B squared equals 1 would be the circle in the AB plane centred at the origin with radius 1. If A squared plus B squared is bigger than that, that means I'm really further away than 1. And likewise, this one means that AB is inside the circle with radius 9. So not 81, because remember that would correspond to the square of the radius of the circle in the AB plane, centred at the origin. So we can sketch this. So we've essentially just got a sort of donut shape made by the region that's inside one circle but outside another. So we don't need to do this tremendously to scale. So if I've got, let's say this is my little unit circle, and I know this isn't quite to scale, but let's say my radius 9 circle is here. 9, 9, minus 9, minus 9, 1, 1, minus 1, minus 1. What we're allowed to have is essentially, well, it's called an annulus, where you've got two concentric circles, and you're taking the sort of donut shape that you get from the region inside one, but outside the other. So that is where AB is allowed to live. Now, having identified that, we need to go back into the language of probability. So they say that every point in the region -2 to 2, -3 to 3 is equally likely to be chosen. Well, surely that means the probability that I pick a good point is just going to be the proportion of the area here, which is good. because if I'm equally likely to pick any point, the probability that my point lies in a given region is obviously going to be proportional to the area of that region. So if I now mark on, let's see, I think it was A could go from -2 to 2. I should note, of course, I've done X and Y, but it's really A and B. So if A can go from -2 to 2, and B can go from -3 to 3, I'm only interested in this region. So if I want the probability, I'm just going to do the area of the good bit, the shaded bit within that region, because that's the amount, those are the points I'm allowed to pick, divided by the total area of that rectangle, because that's the proportion of the area which is okay. So obviously the good area is going to be the area of the rectangle. So let's see, because it goes -2 to 2, -2 to 2, this is going to have length 4, this is going to have height 6. So we're going to have 4 times 6, but then we're missing that little unit circle. So a unit circle has a radius pi1², which is pi, and then we divide that by the total region of the relevant area, which is this rectangle, which is 4 times 6. So that is 24 minus pi over 24. Is that an option? Yes. So the correct answer is F. In this question, we're told n is the number of intersections between these two fairly simple modulus graphs. A is a real number, and I guess we're supposed to imagine A taking different values to give different possible numbers of intersections. We need to decide what's the smallest impossible value of n. So what's the smallest number of intersections which cannot be achieved across all A. So I guess we should begin by just sketching each of these graphs individually, and then we can think about how they'll fit together for different choices of A. I mean, the fact they're talking about intersections of graphs indicates that probably this isn't designed to be done in an algebraic way. And also, these graphs are both very, very simple, so I think there's no reason not to just sketch them. So let's start with the quadratic one. So one of the graphs, the quadratic one, was modulus x² minus a². So if I didn't have a modulus there, then what would that look like? Well, it would obviously have x-intercept at a and minus a, and it would have y-intercept down at minus a² if the modulus wasn't there. So that would give me something like this. And then to obtain the version with the modulus, all that happens is the portions which are negative now get reflected in the x-axis to turn them positive. So we get this very, very simple shape. Y-intercept now up at a². So that's y equals modulus of x² minus a². The other graph was y equals a² modulus x minus 1. So that's even easier to sketch, because without the modulus, it would just be a simple straight line. So specifically, it would be a straight line with x-intercept at 1, and then the y-intercept would have been at minus a². If you imagine there's no modulus there and you plug x equals 0 in, that's what you get. So that would have been something like this, where that would have been minus a², that's 1. But then again, in order to account for the modulus, what we actually have to do is reflect that negative portion. And that gives us this really typical V shape. So obviously this isn't perfectly to scale, although it may not look like the mirror image of that. This is clearly meant to be a². Okay, so does anything stand out about these graphs? Well, they've got the same y-intercept, which is pretty interesting. So they've got the same y-intercept. That means that if I did only want to have one solution, I would need to have no other intersections. That doesn't seem possible, because if I put a V-shaped graph in here, how can I help but cut again, right? I mean, I guess I could try, well, that's flat, so I'm going to have to come down and cut it at some point. No matter how I imagine moving A to scale these things, obviously this thing, the V, has to touch at 1, but I can draw that in different places to account for this A secretly being in a different place. It doesn't look like it's possible. And I mean, moreover, I guess as well as the fact we're forced to cut at some point to the right, we're also going to have another cut somewhere to the left, as in for negative x, because this is quadratic and the V is linear, and a quadratic's always going to overtake a linear function. So it looks like we cannot help but have more intersections, and it might be very tempting to then put this. That seems too easy for the last question of the paper. So is there any loophole? I mean, is there any case we've not considered? Well, what if A is 0? A is 0 is a pretty extreme case because it turns that just into the x-axis, right? So maybe we should think about the a equals 0 case as a loophole. Simply because we're looking for a loophole because the answer n equals 1 seems too easy. Well, if a is 0, one of my graphs is just the x-axis, and the other one, this, is just x squared. That really does have just one solution. So actually, n equals 1 is going to be possible. However, we can see that n equals 2 is not, because we've just observed that you definitely have to have at least one cut over here. In fact, possibly even 2. I guess you could manage to just have one, seemingly, if you did that something. But then we also know, because the quadratic's going to overtake it, there's going to be at least one other to the left. So there's at least one to the left, at least one to the right, and the y-intercept. There's definitely no way we could only have 2. So the answer's B. That was a bit of a trap, I think, with the weird a equals 0 case, but they will set these types of mean problems towards the end of the paper, and we should be alert.